Hello everyone, welcome back to Complex Differential Geometry. Today we're going to be looking at exterior differential forms. This is lecture 6, and this is again going to be a pre-recorded video because the original take in the live session felt a little bit too jumbled, so I'm going to try to record this again. So let's start with a brief recap of what we did last time. First of all, we defined an almost complex structure, called an ACS, that was a 1-1 tensor field. It was a complex structure on each TPM. And it was the answer to the question, if I have a manifold and I add a holomorphic chart, holomorphic atlas, then I can define something called a complex structure on the manifold, right? So we were asking, well, what if instead of looking at this picture where we have the whole manifold, we look at the parts. We think of it as a set of points. I'm going to just draw them as these little dots. So these are all the points on the manifold. And what if we defined complex structures on the vector spaces on each of these points, right, on the fibers? Could we integrate them together to get a complex structure on the manifold? That was our question. We then called this manifold with an almost complex structure. I almost called it an omelet structure. With an almost complex structure, we called it an almost complex manifold. And our question was, are all almost complex manifolds integrable? Can we integrate all of these points, all of the complex structures on these points to get an overall complex structure on the manifold? Yeah, integrable. So the answer is not always. Right? And when is it then? So when? That's when the Nienhaus tensor is 0, which is equivalent to saying that the holomorphic tangent vectors don't change along anti-holomorphic directions. I won't write that whole thing, anti-holomorphic directions. And we translated that to this idea that, to put it rigorously, xy, if they're an element of this bundle T10M, then that implies that their Lie bracket of x and y must also be in this same bundle, the subbundle of holomorphic vectors. And we showed that this is equivalent to the Nienhaus tensor being 0, because the Nienhaus tensor is 0 precisely when this condition is met. So now we know when precisely an almost complex manifold has an integrable almost complex structure. So when that happens, it becomes a complex manifold, or is admissible as a complex manifold, becomes a complex manifold. So today we're going to talk about a powerful tool that we can define on almost complex manifolds. So that's why we talked so far about almost complex manifolds and why, when is J-twiddle integrable. So let's say that I have an almost complex manifold, then I have something called well, first things first, let's say that we have a tensor, we have something called a tensor algebra. We're going to this is going to be a little roadmap for what we're going to do. So we're going to have a tensor algebra, and then from the tensor algebra, we're going to refine, and we're going to form a subalgebra called the exterior algebra, the exterior form algebra to be specific. And as you can imagine, the elements of this algebra are called exterior forms. So Neon was asking on the Discord, what's the difference between an exterior form and an exterior differential form? So here's the key difference. So then we go to the bundle, right? Like we aggregate these. These are pointwise defined. These are pointwise. So then we get something called the exterior form bundle. And then if we take a smooth section off of this bundle, we get something called an exterior differential form. So that's the difference. This space would be lambda of TP star M. That's what it's called. This space is called lambda of T star M. So we have removed the P because we no longer are assigning to a single point. And then this would be the sections on that. So essentially, we get this. So that's the difference between these two. So let's talk about tensor algebras, and let's go from there. So in order to start talking about tensor algebras, let's like briefly review what a tensor is. So if wrong color, SP, let's say that SP is an element of TRS at P of M, then that means that SP is a multilinear map of this type, T TPM, or something that takes TPM, TP star M, R times, cross something that takes TPM, elements from TPM, S times, and returns something in the real numbers. Yeah, so we're going to be starting off with real numbers right now. So everything we're talking about, it applies to real numbers. We're going to build up to complex differential forms in a little bit. So this is a tensor, right? And so we've looked at different ranked tensors, right? So we have 1, 2, 3, things that are elements of the reals. I suppose you could have 3.3. These are all rank 0, right? They're also called scalars. And then we have VP, which is rank VP and alpha P. These are both rank 1. So I'm talking about their overall rank if you add their contravariant rank to their covariant rank. And then you have higher order tensors like VP tensor alpha P, which is a rank 2 tensor. So today we're going to be talking about how to turn this into an algebra. So in order to do that, we need to know what an algebra is. An algebra is a vector space plus a multiplication, a bilinear operation, and that is called a multiplication. And this multiplication, amongst a lot of things, particularly needs to be closed. So this is a multiplication of elements of the algebra. So not just scalar multiplication, but multiplication of the vectors themselves. So that's what we call an algebra in this context. I thought I should clarify because algebra is kind of used in a few different senses in math. So this is the sense of algebra that we're going to be using. So we call a tensor algebra curly T. Let me try to draw a curly T. This is not a tau, it's a curly T. Let's define it over TPM. So in general, this could be V, generic vector space, but we care about mostly over TPM. So this is defined as the direct sum of all r greater than 0, s greater than or equal to 0, t, r, s at p on m. So this is the algebra. So what does this mean, right? This means what if we could combine the different rank tensors, right? So an element of this space would look like this. Let's say we had a real number, which would be the 0th rank. So 12 plus VP plus alpha p plus let's say WP tensor beta p and so forth. You could have other types of elements. You could have like AP tensor, BP tensor, xi p. You don't, let's say maybe there isn't anything in the middle, that's fine too. This would be a 2, 1 tensor, right? So these are the kind of elements you would get here. If it's hard to understand this principle, think about the complex numbers. So complex numbers look like x plus I, y, right? So that's where you get r direct sum r. So we get, so that corresponds to this r corresponds to this number, and this r corresponds to this number. And so that's where you can see that like this sum over here is going to be something like real, well, it's going to be T00, which is which we're going to define as the field, which in this case is still real, of P at M. And then we need to put T11. So like we're just substituting R and S over here, right? So P of M plus we get, oh sorry, this should not be 1, 1. I mindlessly said that. So T01, T01, P on M, and so forth, higher order tensors. So for example, this VP is from here, and this alpha P is from here, and these would be from further. We need all of them, right? Because in order for the multiplication to be closed, since we can multiply, let's say we could multiply VP tensor WP, maybe that's a tensor that we have. Then if we wanted to multiply, so good thing I talked about this. So on the algebra we need a product, and that product will be the tensor product. And what it's going to do is, let's say we do this, then it's going to give me a new tensor, which is exactly equal to this. And so we took a rank 1 element, a rank 2 element, 2, 0, and we took a rank 0, 1 element, and then what that will produce is a rank 2, 1 element. We'll add the ranks, right? And we can, so this is the tensor algebra, and it's a graded algebra because this the elements sort into something called a grade. The grade in a graded algebra is, so grade, this is a natural number, and it signifies these, like, so if your algebra is isomorphic to you know, like let's say you have G1 direct sum G, or even should start with G0. So then G1 plus G2 plus, these are just generic spaces, and dot dot dot. So these would be the grade 0, and then these would be grade 1, etc. So in our example, these are the grade 0 elements. Let me highlight that. These are grade 0. These are these are both grade 1, actually. They're so I'll get to that in a little bit. So these are both grade 1. So how do we decide the grade here? The grade is the for an RS tensor will be R plus S. So it's like the overall rank. But grade is not the same thing as rank. In this case, for the specific graded algebra, that's the tensor algebra. The grade is equal to the overall rank. But in general, your grade, obviously, I mean, in a graded algebra, you're not going to have tensors, right? So it's not always going to be tensors. But with these, there are mixed grade elements, mixed grade. In fact, let me not write that here. This is this element that we wrote over here. This is a mixed grade element. So you have grade 0, grade 1, grade 1, grade 2, grade 3. So and not all of these are some of the grades are not fully filled. So some of them are 0. But then you can also have homogeneous elements. So homogeneous elements of grade K. Think of these kind of like homogeneous think of these as homogeneous polynomials. So let's say VP tensor alpha P plus VP tensor WP. So this would be a homogeneous element. And this one would be grade 2. So now that we've talked about grades and gradings, so one last thing, which is that this is grade 2, right? And this is grade 1. And it produces, the tensor product produces a grade 3 element. And this is kind of what gives the grade some meaning, is that the product will add their grades, right? So if that wasn't there, then the grading would be arbitrary. So since there's some logic to the grades, and that if you take a grade P and a grade Q, then the product gives you grade P plus Q. That's what makes this grading meaningful. So now that we've defined a tensor algebra, we would like to restrict our tensor algebra. And if we restrict it in a specific way, keeping only the antisymmetric covariant tensors, we will get something called the exterior form algebra. So that's what we're going to look at next. So the next thing, as we said, is to talk about the exterior form algebra. And we're going to, in order to define this thing, which is going to be a subalgebra of the tensor algebra, we're going to need to define this thing called an alternating map. So the alternating map is a projection that projects the antisymmetric part. part of a tensor. In this case, we're only going to be concerned with x element of T0k, or let me just write it like that, T0k P of M. So these are the 0k tensors. Right. And this alternating map is going to give us the antisymmetric part. So it's this algebra, the exterior algebra is really the algebra of antisymmetric tensors. In this case, antisymmetric covariant tensors. And so let's see how we can construct this. So we're trying to construct the alternating map. So the first thing we need is a way of permuting elements. So let's take sigma element of Sk. What's Sk? It's the group. So we're doing a little bit of group theory now. It's the group of permutations of k elements. In order to construct our antisymmetric element, we're going to need this sigma. Let's define its group action. So how is it going to act on our element? It's going to act by sigma of x is equal to sine of x, sine of sigma times x. And what is this function? It's called the sine function. It returns the sine of the group element. So these are permutations, right? So sine of sigma is equal to +1 or -1 if it's +1 if the permutation is even, and it's -1 if the permutation is odd. So what makes a permutation even and odd? Let's quickly go over that. So let's say that this is our reference permutation. So this is the order that was originally there. So then if I, let's say, go to this ordering, 1, 3, 2, that's one swap. One swap. So this is an odd permutation. This is odd. Sorry. So if I swap 1 and 3 again, then so we have one more swap. This is two swaps so far. Two swaps. So this is an even permutation. So that's how it works. So if you can get from the reference permutation by an even or odd number of swaps, that's what makes it your permutation even or odd. And so this is how sigma is going to work on x. So now we can define the alternating map, which is going to be called AK. AK of x is equal to 1 over k factorial, the sum of sigma element of Sk. So we're taking every permutation from the permutation group on k elements, and we're applying it to x along with the appropriate sign. You might be wondering about this little factor up here. This factor is so that ak after ak of x is equal to ak of x. So that the projection operators, you want them to be something called idempotent. Idempotent. If you project something 2 times, it should give you the same thing as if you project it once. You don't want to lose information on multiple projections. So this is our antisymmetric projection operator or map. So this is something that AK is something that goes from T0K P on X, on M, and arrives at a different one, but these are antisymmetric. This is the antisymmetric subset of that. So this is how we take any old 0k tensor, so our k covariant tensor, and turn it into an antisymmetric one. And our exterior algebra, exterior, it's the algebra of antisymmetric uh, 0k tensors. It's called lambda k of TP star m. TP star m because we're talking about covariant objects, and the k is what comes over here. So this is it. Our exterior, this is called the exterior form algebra. And there's a similar thing called, if you did this with k0 tensors, then you would get something called the exterior vector algebra. Exterior vector algebra. There's more on this in Chern, Chin, and Lam, page number 57. So if you want to look at that, you can look at that. The notation is slightly different from what I'm using here. We're not going to talk about this too much more because we're not really going to need exterior vectors, but we are going to need these things called exterior forms. So that's what we're going to focus in on. So the full exterior algebra is lambda of TP star m, and that's equal to the direct sum of k equals to 0 to infinity, or sorry, to the dimension of the underlying vector space TP star m, where well, so that's basically just dimension of m, right? So of these individual lambda k TP star m's. This is the same idea where we're taking forms of different degrees and we're adding them all up together to get our overall space. So this still needs a product, right? So if you're observant, you maybe have realized that the tensor product is going to take us out of the space because the tensor product doesn't care whether an element is symmetric or antisymmetric or anything. So we need to come up with a product that will preserve our antisymmetry. So we're going to call that the exterior product. Exterior product. So the exterior product, it's also called the wedge product because that's what it's usually denoted by, a wedge. So the wedge goes from lambda r of TP star m cross lambda s TP star m. So an R form and an S form. So maybe I forgot to mention this. So the elements of these are called exterior K forms, right? So we have a R form, an exterior R form, and an exterior S form. And that is going to give us an exterior R plus S form. That's a map that we are going to have to define. How do we define that? Well, if alpha p and beta p are two R forms, is an R form and an S form, then we say that this is equal to, well, we could just make it the tensor product of it, right? But then there's the problem, right? We're going to exit out of the algebra in general. For two generic elements, we may very well exit out. So we just take the alternating map of the result so that we project back down into the algebra. And that's our definition for the wedge product or the exterior product. So let's look at some of the properties. Let's look at some of the properties of the wedge product. So one, it's distributive. So that means I'll write one of these to get so that you get the idea. So psi1 plus psi2 wedge eta is equal to xi1 wedge eta plus xi2 wedge eta. And there's another one that looks like xi wedge. Let's just do both of them. Why not? Plus eta 2 is equal to xi wedge eta 1 plus xi wedge eta 2. That's distributivity. They're anti-commutative. Anti-commutative. This comes with the whole anti-symmetry thing. So if xi wedge eta is equal, if we want to swap them, then we have to gain a minus sign that respects the grading of these elements. So rs eta wedge psi. And number 3, they're associative, or the product is associative. So that means that if we have 3 forms wedged together, xi wedge eta wedge zeta, then that's equal to xi wedge eta wedge zeta, but on this side we evaluate xi wedge eta first, and on the right hand side we evaluate eta wedge zeta first. So these are the 3 properties of this exterior product, and this will make sure that our algebra is closed. Ensures our algebra is closed. There we go. So the next step is, so now that we have the exterior form algebra, the next thing that we want to do is we want to define exterior differential forms. So first of all, we will need to define a bundle. So let's define the exterior form bundle. And so this is going to be the kth exterior form bundle, and it's going to be the vector bundle on M whose fibers are lambda k tp star M. And we call this space, this whole space, we call it lambda k of t star M. So that's the second thing that we were talking about at the prelude to this episode, right? We were talking about how this was the space that the exterior form bundle would be. So this is called the kth exterior form bundle. And it's to recap what we were talking about with vector bundles is that the vector bundle is an aggregation of all the fibers. So this is what we would consider the fiber here, right? So if we merge them all together, we get this bundle, and we want to take a section out of this bundle. So if we take a section out of this bundle, what happens? So let's say take a section out of lambda k t star M. Let's assume that this section is smooth. So then we define this to be omega k of M. This is a big moment. This is what we want. But this is still real. So this is a real exterior differential K form. Now, we've gotten a bit abstract, so let's think about what we've just done so far. So let's say we have the manifold. We have a point P on the manifold. We had a fiber. What was that fiber? Our fiber was our algebra. So this was lambda K of TP star M. We know that, and so the reason that that works is because an algebra is a vector space, right? So we can use it as our fiber. Uh, it's a vector space that's even more restricted. That doesn't matter to us. And then we take the bundle of all of those fibers. That creates this block looking thing. The block could be twisted. I'm not going to draw it twisted just for illustration purposes. So let me highlight this fiber specifically. That's my fiber. So then, so this bundle is what we're calling lambda K of T star M, right? And then we took, let me find another nice color here. Then we took a smooth section out of this bundle. This smooth section is what we call, this is this thing, a real exterior differential K form. It's a covector field form. That's why we were talking about covariant tensors, right? A K form is a 0K covector field. A 0K tensor, or a rank K covector field. You could think of it in any of those ways, whatever suits your fancy. So that's what we have over here. So I really want to hammer home this idea that what exactly is a form, because a form is a kind of a nebulous word here. Since we've already done so much work in trying to understand what a tensor is, I want it to be clear that a form is just a special name for a specific kind of tensor. So when you hear this thing differential form, underlying it is just a tensor at the end of the day. That's what I want to make clear here. Okay, so now that we have real exterior differential forms, differential being the operant word there, we have something that's smooth, a smooth section. So that allows us to define some sort of derivative on that object. So we very aptly call this an exterior derivative. So how do we define this derivative? Well, remember that we had these things called the differential of a map, right, at a point. And then we use these to define covectors. And then the field version of a covector is a one form. This word now is going to pay off, right? So the reason we called it a one form is because it's actually this thing, and the reason why we called this small letter d is because this is the exterior derivative. We wanted to make sure that this letter would agree with what we were eventually going to define. So d is a map that goes from omega k on m. Remember, omega k, that's these sections, these smooth sections, and the derivative will increase the grade or the degree of these. So it'll give you a k plus 1 form from there. And so if we think about some of the properties of this, number one, it has a graded Leibniz rule. Graded Leibniz rule. So what that means is that So a Leibniz rule is how do you apply the derivative over a product, right? So let's say I am applying it over my product, which is going to be the exterior product since we're in the exterior algebra. So this is equal to d alpha wedge beta. Yeah, so when we apply, yeah, that's something I should talk about. So if I apply the exterior derivative, then what I get is called d alpha. That's where this whole thing uh, kind of corresponds to what we're doing right now. So then that is plus minus 1. So there's some factor that we need to put here for the grading so that the antisymmetry all work out. So that's this factor here. It's the degree of the form alpha. So whatever this is maybe, let's say this is a, a p form, then this would be p, right? Then this would be p. So that's what I'm saying here. So alpha and then wedge d beta. It's very much like you could say that this is the graded version of something that looks like um, mm, if I were to take like partial x of fg, then I would have something like partial f partial x dot g plus partial plus f dot partial g partial x, right? So this is essentially the upgraded version of that idea. So that's what we're doing there. And secondly, it squares to 0. There's a very interesting geometric interpretation of this that we're going to get into when we talk about cohomology, but not now. But for now, let's just say that d square is equal to 0. So if I apply d square on any differential form, I'll get 0. And thirdly is this thing where d f, where f is an element of C infinity m, which is by definition lambda 0 of t star m, then df is just the differential of the map as in lecture 1. I noticed that you have to do some finagling of the definition because we never formally defined it for a vector field or a covector field. So yeah, wherever there are p's, like whenever we say something like dfp, you have to convert that in your mind to df, and then you'll get the equivalent. So that's the way that it works on the the zero forms. So which are these are the zero forms. Right. So that's the exterior derivative. Now all that's left is to do the task of the last part, which is like this real part. We need to turn this into complex. So that's the last thing we're going to do. And then we're going to do the rest of this in the second part of this lecture. It turns out to be pretty long. Before we conclude, though, we have one step left, which is turning the real forms that we have so far into complex forms. So let's talk about this idea of complexification. So we're going to complexify our forms. How does that look like? Well, instead of being real valued, now they're just going to be complex valued. So where the tensors were going to be outputting in R, now they're going to be outputting in C, and their coefficients are going to be in C and all that kind of stuff. So it just very cleanly amounts to, we're going to call it this, we're going to call it lambda k complex of I'm calling it V, TP star M, which is defined to be what we had so far, which is the kth homogeneous algebra, TP star M. Real tensor product with, or real direct product with C. That is the complexified space, right? Like just like any other complexification. So this is the space of complex valued forms. Complex is the full space that we want, right? You could, yeah, complex valued. Oh, these are complex valued exterior forms. I was about to say that these are complex valued differential forms. They're not. We haven't defined the differential forms yet. So these are complex valued exterior forms. And now we're going to extend this to differential forms. So before we do that, we're going to first say, let's say that T star M cross C, we know that this is isomorphic. This is the complexified cotangent bundle. So complexified cotangent bundle. So that's just a fancy way of saying that we turn the cotangent bundle into a complex space. So then this is given by, remember, so this is where that, remember we were doing all of this stuff to decompose V star O times C was isomorphic to V star 1, 0, O plus V star 0, 1. Well, now that's going to pay off. We're going to use this result here. This is where this is going to pay off. So this is going to be equal to T star 1, 0 M plus T star 0, 1 M. So these are the holomorphic and anti-holomorphic cotangent bundles, right? So these are the holomorphic and anti-holomorphic cotangent bundles. So then this is what is going to allow us to decompose these complex exterior forms. This is one of the key results that we're building up to. So right. So then this was the pointwise definition. If we remove the pointwise definition, what do we get? We get lambda k c of T star M, which is the same thing as saying lambda k of T star M, real direct product with C, which is isomorphic to, we just take the lambda of this whole thing. So let me just copy that. This will not backfire in any way, shape, or form. It already backfired. Oh no. So then this is equal to lambda k T star M, sorry, T star 1, 0 of M, right? The holomorphic tangent bundle. Direct sum, lambda k T star 0, 1 M. And that is how we're going to find these building blocks. So these are our two building blocks. These are the holomorphic K-forms, and these are the antiholomorphic K-forms. But what if they weren't both K-forms, right? Uh, in fact, on any almost complex manifold, what we can do is we can define this space, lambda complex K of T, or sorry, P comma Q. This is the big result we're going to go for in this lecture, which is that um, we can say that this is equal to lambda P of T star 1, 0, M plus lambda Q of T star 0, 1, M. So here K was equal, but here they're not. And in general, lambda K C of T star M is equal to the direct sum P plus Q is equal to K of lambda, this space. I'm going to explain this in a moment. Let me just write it out. So T star M. So basically what we're saying is that for all combinations PQ, where PQ is equal to K, if we took all of them, so let's say that K is equal to 3, for example, then we would have 0, 3, we would have 1, 2, we would have 2, 1, and then we would have 3, 0. So all these kind of forms, right? So these will all add up to each other to give us the kth complex, the kth complex exterior bundle. So that's what this is. This is a very important result, so I'm going to box it. I don't know if the red is very apparent on the screen, but yeah, this is very important name, PQ. Let me do it in a brighter color so that it's I know it's visible. So this is called PQ decomposition. It's a very important result. Let me underscore that again, just because it's so important. So the fact that we can decompose the kth exterior form bundle into this so this space, yeah, I should mention that this space, this thing is called, this thing is called, in fact, let me not do that whole thing. Let me just say it here. This is called a bigrading. Remember, we've already talked about grading. So this is a bigrading. P is a grade, Q is a grade, and we've stuck them together. So now it's a bigraded space. And the fact that we can bigrade this space and we can find bigrades under this space is precisely the point of PQ decomposition. And it will, the fact that one of the sides, the P side is holomorphic and the Q side is anti-holomorphic, will make this like a very powerful decomposition technique. And so one thing I just want everyone to be careful of is that we have now RS tensors, and we have PQ forms, right? And PQ forms are still tensors, so be careful. So PQ forms are 0 P plus Q tensors. Right? They're covariant tensors where P and Q have to add up to give you the covariant rank of the tensor. So this is with respect to the complex structure. Complex structure. And this is with respect to tensor. This is the tensor's rank, right? Uh, it is how many inputs the tensor takes. So uh, respecting whether or not it's contravariant or covariant inputs. So please be careful. You'll see both of these, and what's extra bad about it is that the forms are also tensors. So the forms actually have a tensor rank in addition to having a complex bigrade. So please be careful. I tried to make the notation distinct in the lecture notes. That's why I went back to using this kind of notation for the tensor space, and for the forms I always make it look like this, so you can know that this is the tensor's rank versus this is the complex bigrade. So hopefully that makes it clear. Yeah, so this is called PQ decomposition. It's the last thing that we're going to look at. We're going to continue next time when we start talking about the power of PQ decomposition on almost starting from almost complex manifolds where it doesn't very cleanly divide the exterior derivative. So okay, let's go to the next page and let me talk about this for real. So we have the exterior derivative, right? Um, so if J twiddle is integrable, then uh, D decomposes into these two uh, new operators. These are called Dolbeau operators. Let me see if I can BA. That doesn't look right. Dol. There we go. Dolbeau. Did I get that right? I'm gonna I'm gonna cheat. I'm gonna look at it. Look it up. Absolutely not. So these are called the Dolbeau operators. And as you might imagine, they are very important to Dolbeau cohomology. And this is going to be an interesting thing where we're only guaranteed to have this clean decomposition if we're on a complex manifold. So like if this is true, then we're on a complex manifold. Complex manifold. So then we get this clean decomposition. So then we so then D has this very simple form that allows us to do some powerful things. So this is what we're going to be looking at in the next half of the lecture. So let's recap. Let's recap what we've done so far. We first defined tensor algebras. And so those the elements of those kind of look like this: VP plus alpha P, etc., etc. And then we went to exterior algebras. Exterior algebras. And this is where we enforce antisymmetry, or project, let's say project the antisymmetric part. Project the antisymmetric part. That gives us an exterior algebra. Maybe we should specify that we are working with the exterior form algebra. And here's where we got exterior forms. So so to be specific, they're called exterior forms once you project down to the antisymmetric part. Before that, they're just forms. So now you have exterior forms, and then we go to the bundle. The bundle is the exterior form bundle. And then we take a smooth section, smooth section, which gave us our exterior differential form. Differential form. In general, it would be an exterior differential K-form. And then, with the exterior differential K-form, we then complexified it. So then we did some complexification. Sorry, this flow diagram is not very balanced, but it'll have to do. So complexification is what we did. And then we had our final tool, complex exterior. I'm going to write its full government given name only once. Exterior differential form. That's a lie. I'm probably going to write this again in the future. Differential form. And lastly, we looked at the fact that complex differential K-form can then be broken up into a holomorphic P-form and plus, or times, I guess, an anti-holomorphic Q-form. And this is called PQ decomposition. It works on any almost complex manifold. That's why almost complex manifolds were so important. Even if J-twiddle is not integrable, you can still do this decomposition. What you can't do on a almost complex manifold is say that D is equal to partial plus partial bar. That's going to require you to be a complex manifold. And we'll see the proof of this in the next part of the lecture. Complex manifold. Or requires, because it requires J-twiddle to be integrable. So we'll look at that next time. All right, so that's it for today. Goodbye, everyone. Hopefully we'll see each other on Lecture 6, Part 2.